In this video, we'll discuss a project called as employee salary prediction using regression. So this is the code to import the required libraries like NumPy, Pandas, some modules from sklearn, matplotlib. So just run this. Right? Then we have a dataset called as salary dataset. This dataset has been downloaded from Kaggle. You can go to Kaggle and there you can type salary dataset. You will get this dataset. Download this dataset, upload this dataset in this Jupyter notebook. I'm using this Jupyter notebook. Upload this dataset in Jupyter notebook. Then read this dataset is a CSV file. Okay? So read this CSV file in a data frame by using read CSV function of pandas. So pd.read_csv. PD is the acronym for pandas, right? Because we have imported pandas as PD. So pd.read_csv salary dataset.csv will read the salary dataset as a data frame, and the name of this data frame is data. Then we'll see what are the how does our dataset look like. So this is our dataset. Data.head will return us the first 5 rows in the dataset. So we have 3 columns here: unnamed, 0, years of experience, and salary. This unnamed 0 column is appearing or coming because this salary dataset.csv file was saved from the data frame to CSV file. It was saved by somebody uh, uh, from data frame to CSV file, and because of that, uh, this unnamed 0 column is coming. So we don't want this unnamed 0 column, we want to drop this column. So data dot drop columns is equal to unnamed 0, in place is equal to true. In place is equal to true means this change will be a permanent change. So this column will be dropped. Now we have only 2 columns left. Data.head will return us this. Right? You can see you have only 2 columns now: years of experience and salary. Then we want to see the details about our data set. So we can say data.describe. This will return us this result. Let me execute this code. So now if we want to look at the details of your data set, right? You say data.describe. That means how many this count will return, how many null value, how many non-null values are there in this column years of experience. There are 30 non-null values in this column years of experience. Similarly, this salary column is saying that there are 30 non-null values in the salary column. So mean will return the mean of this column. So it is 5.4 something. So salary, this is the mean salary. This is the standard deviation. This is the standard deviation of years of experience, standard deviation of year salary. This mean will return the minimum value in this column, right? So minimum salary is 37,732. So this is the 25th percentile of this column, or the first quartile it is called as. The salary column's 25th percentile is 56,721. Similarly, this is the 50th percentile. This is the 75th percentile, and this is the max value in this column. That means max experience is 10.6 years, and max salary is this much, right? So this gives the overall idea about our data set. Now we want to check if our column contains some null values. So for that, we'll call this function is null on our data frame. So data dot is null dot sum. So this sum will sum the null values in each column, right? So in years of experience column, we have zero null values. In salary column, we have zero null values again. Now, if there are null values, we want to replace those null values. The simple strategy used here is replacing the null value by the mean of the column. So we have imputer, right? To this is just a name given to a imputer. There is a simple imputer. uh, we are uh, building an object of this simple imputer. So strategy is mean. That means this will build an imputer which will replace the missing value or null value by the mean of that particular column. So now here you see, look at this code. So this data of years of experience dot values, this will return the values in the years of experience, right? This will return a numpy array of the values in the years of experience column, right? So this is a numpy array. So this fit transfer function requires this numpy array, this input in a 2D format. So that's why we are converting this. That's why we are converting this into a 2D format by using this reshape function. This reshape -1 comma 1 says that keep the number of rows as it is. -1 says keep the number of rows as it is, and there is only one column, right? So even though there is only one column, it's a 2D. We are converting this into 2D. We are converting this into 2D. This will return us the numpy array with it's a simple array. We are converting that into 2D, right? And then we are passing it to fit transform. So on imputer we are calling fit transform. So this fit transform function will apply this imputer and will replace the null values in the years of experience with the mean of this column. Similarly, we are applying this imputer to data of salary column. Again, this data of salary dot values will return a numpy array. This fit transform requires this this input to be in 2D format. So that's why we are converting it by using this reshape function and then applying this imputer. So and then storing that in a data of salary column, right? After applying the imputer, we are again storing this in this data of salary, that is the salary column in the same data frame. Then we want to split our data set into x and y. So where y will be the output variable or target variable, and where x will be the features. So x is equal to data of years of experience. We are having only years of experience as the feature. So we are retrieving that. This values will return us it in a numpy array. Then again we are converting that into 2D array, because most of the machine learning models requires the input uh, feature feature inputs as the 2D matrix, right? That's why we need to convert this into a 2D matrix or 2D 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 array. So this reshape will convert this 1D numpy array into 2D matrix. So where we have only one column. Then we are having y, that is dependent variable column, as a salary column, right? The salary, data of salary, we are storing in y, data of salary, that is salary column we are storing in y. Then we are doing feature scaling. Now why is feature scaling is required? Feature scaling means, I'll show you an example. Just a moment. So here is an example of feature scaling. Let's say you have this data set where we have heights and weights Right? If you see, the height is varying between a small range from 1.7 to 1.8, whereas this weight is varying from 68 to 78, right? So this, now there is a huge difference between heights and weights, right? The range in which the height is varying and the range in which the weights are varying. Now, if we use these inputs as it is, right? So, most of the algorithms or the algorithms like k-nearest neighbors who relies on the distances will be dominated by the larger value column like this weight, right? So because the numbers are larger here, right? That's why we need to convert this weight column, which will be in the same range or approximately or nearly in the same range of this height. So after scaling, after applying scaling on this weight and height column, we'll have this uh, height column like this after scaling and weight column like this after scaling. Now, if you look at these two columns, they are varying in the nearly same range. They are varying in the same range, right? There is not much difference in that. So that's why this is called as scaling, making making all the variables vary in approximately same range. So we apply the standard scalar. I'm sorry, I did not execute this. Then we will split our data set into training and testing data set. So x train, x test, y test is equal to train test split. By using this function train test split, we are converting x and y. We are splitting x and y into training and testing. So we have four variables here: x train, x test, y train, y test. Right. So and that this x and y is being splitted into these four by using this train test split. Now test size is 0.2. That means the test data set out of test data set will be 20% of the whole, right? So size of the testing data set will be 20%. That means this x test will be 20% of this x, and y test will be 20% of this y, and x train will be 80%, and y train will be 80% of this y. Okay. So random state, make sure that every time you do the split, you get the same split. You get the same split, meaning that, let me see if I have an example here. Don't have an example. So meaning that, every time you do the splitting of the data, you will get the same split as x train and x test, y train and y test. This random state, make sure that. Then we create the linear regressor model by using this linear regression. We are uh, creating an object of this linear regression, and this object is called as regressor. Then we are calling this fit function. That means we are training our model. We are training our regression model. Regressor.fit. We are passing x train and y train. So we did this split, then we created the linear regressor model. So this is the linear regressor model. Now we are predicting the values for x test. We are passing the x test to this predict function called on this regressor, which we created here, right? So this the values written by this regressor are stored in ypred. Right? Values written by the regressor dot predict function are stored in this ypred, right? Then we'll visualize our training set results. So you see, this is the training test result, right? So what this code doing is plt.scatter will create a scatter plot of x train and y train with color red. So these are the red points which you are seeing These are the training points, X train and Y train. So the color is red. So plt.plot function will plot X train versus the predicted X train. So this is predicted Y train. Right? So this function is predicting the Y values for this X train values. This predict function is predicting the Y values for this X train values, and we are plotting those in blue color. So these are the predicted values. Actually, this blue line which you are able to see, these are the predicted values for this X train values, predicted Y values. These are the predicted Y values for the X train values, and these are the actual Y values, right? For example, if you consider this point here, right? So this is the actual point, and this is the predicted point here. Predicted points are always on this line. So the difference between these two, predicted and actual, are called as the error. Right? So the title of the plot is salary versus experience. Then X label is years of experience. Y label is salary, and plt.show will show this plot. Similarly, we are plotting the test set result. Now, again, scatter X test and Y test. We are plotting X test and Y test with color red, right? So these red points which you are able to see, these are X test versus Y test. Now we are passing the X train to the regressor, and we are looking at what are the Y values for this X train, right? So we are passing this to the regressor and asking the regressor to predict the Y values for the X train, and we are having the color blue. So these are the predicted Y values plotted here. Right? Then again, title, X label, Y label, etc. Then we will calculate the mean squared error between Y test and Y predict. This is actual Y's and predicted Y's, right? Actual Y's and predicted Y's. Actual salary and predicted salary, right? Y is storing the salary, actual salary and predicted salary. So mean squared error will return us this. Let me run this. So now I want to also calculate the mean squared error, root mean squared error. Right? So how to get the root mean squared error? Because root mean squared error is more intuitive, right? So I'll just take the square root of this MSC, mean squared error, right? So what is mean squared error? It is the mean of the errors, square errors, right? So what are the errors? So if you consider this data set, so this is the predicted value, this is the actual value. So we take the difference between that. So the difference is 5, right? 140 minus 150 minus 140, 10, right? By you can do either way because we are taking mod of that, right? Then 200 minus 170, 30, right? So we are taking the errors, right? And MSC calculation, we are doing the squares of this error. So this is the MSC calculation. We are making the squares of these errors, right? And we are dividing it by the number of data points. There are 5 data points, so that we can get the mean of this squared error. So mean squared error is 8380, and root mean squared error is the root of this, square root of this, right? If we take the square root of this, we will get 91.54. The root mean squared error, right? So that is more intuitive. That it says that on an average, the difference between the actual values and the predicted values is 3580. Similarly, we can calculate the mean absolute error. The mean absolute error calculation is we have these errors, right? Just add all of those errors and divide it by 5, right? In mean squared errors, we are squaring the errors, adding all those and divide by 5, right? So mean absolute error, mean squared error, and root mean squared error. These are the mainly used um, error calculation, or to see the performance of the model. So If I summarize, the meaning of this is this error is the difference between actual values and the predicted values. Actual salaries and predicted salaries on an average is 2446. That means the actual values and predicted values on an average are differing by 2446. So that was a simple project for predicting the employee salaries using regression. So thank you so much for watching. Thank you.